Alright, so next we are going to talk about how we can tell if something is insoluble or soluble. And this can actually be something that's measured. Like you could talk about different levels of solubility, you can talk about numerically. We're not going to do that. We're just going to roughly eyeball it in this class. And we're going to really lean on attractive forces for this. So all those ideas like ion-ion, dipole-dipole, hydrogen bonding, dispersion forces, those are all going to come into play here. That idea is going to be a very strong thread throughout this video. So the first rule, and I say it like there's a second, but there's only one when we're talking about this. So the first rule of solubility. This is what you want to stick in your head here. Do not forget this. First rule of solubility. Like dissolves like. It's as simple as that. You look for a nice matchup of attractive forces. So polar solvents are going to dissolve polar solutes really nicely. Nonpolar solvents are going to dissolve nonpolar solutes very nicely. They're going to mix and make solutions. But if you have something that's polar and nonpolar, they're not going to mix. They're going to separate. Oil is nonpolar. Water is polar. They don't mix. But water and sugar are polar. We saw them mix. Acetic acid is a polar molecule. It mixes in water very nicely. It gives us vinegar. If you've ever used like Goo Gone to get rid of a sticker or something like that, or sometimes you can use just olive oil instead. Goo Gone's a little cleaner because it's a thinner oil. The sticker glue is nonpolar. And so you use a nonpolar solvent and you get off it. You can use WD-40 or something like that too. Any sort of oil will remove those sticker materials, but water won't. You can run under a sink forever. Water's a polar solvent. It's not going to take that sticker material off. And that's just coming back to this like dissolves like. So, just to be clear, if you got a polar solvent, like water, remember we talked early on, water has that bent geometry which makes it polar molecule, makes it a polar solvent. It's going to dissolve, or polar solvent dissolves polar molecules. Okay? So guess what a nonpolar solvent does? That's right. It's going to dissolve nonpolar molecules. So, we kind of just break it down this way. Now you can look at hydrogen bonding as well. Like that's a really nice, if that really clicks, then you're going to have even more solubility. But just something that's polar and hydrogen bonds is going to dissolve something that's polar. So we're really just going to break down on polar versus non-polar here. But you want to be able to recognize those things. And you're going to maybe be thinking, hey, what about ions? Well, that's the next video. We're going to talk about ions in the next video. But that's what we're talking about here. So, for example, I'm going to draw two different molecules. These are both biologically active molecules. I'll write their names underneath in a second, but you don't have to know them. Okay, and we've got 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That's an OH on the end. That's a double bond. That's a double bond. That's a double bond. That's a double bond. And we got side chains there and there. And we got one down here. Okay. You totally know this when you see it, I'm sure. You're like, oh, I know, that is vitamin A. I know vitamin A when I see it. There's vitamin A. Okay, I'm going to draw another vitamin over here. Oops. That's supposed to be an O. We'll just start over from scratch. There we go. Alright. Can't really erase a Sharpie. You can actually clean it off glass with acetone, if you didn't know that. Old organic chemistry lab trick. You can label everything with Sharpies and actually remove it. So if you have like acetone nail polish remover or something like that, you can actually get Sharpie off of glass. Might be the most useful thing some of you learn in this class, was that little blurb I just said. Who knows? Alright, that'll be the test. I just mail you a piece of glass with a bunch of stuff written on it. You have to clean it off and mail it back. Alright, so this is vitamin C. Alright, so you got vitamin A, vitamin C. I can make a bunch of jokes about a late 90s, early 2000s pop singer, but I wouldn't want you to look that music up and get subjected to it. You'd think less of an entire generation from that. So, vitamin C and vitamin A. One of these is water soluble. The other one is what we call a fat soluble vitamin. So one of them dissolves in water, one of them dissolves in oils and fats. So oils and fats are nonpolar. And you can think of it as like a nonpolar solvent because they're a liquid. So this is like a nonpolar solvent. And water, as has been discussed ad nauseum, is a polar solvent. So with that knowledge, we can look at these and determine which one is fat soluble, which one is water soluble, based on which one matches up with intermolecular forces better. So remember that carbon-carbon bonds are nonpolar, carbon-hydrogen bonds are nonpolar, so this whole thing over here has a bunch of nonpolar area. You see this right here? This little OH, like, yeah, okay, that's a little bit polar, but it's only a little bit. Like, there's only this little range right here compared to the whole rest of the molecule that's nonpolar. So guess what this is? This is a nonpolar molecule. We get over to vitamin C. This is polar, this is polar. We got polarity over here, we got polarity, polarity. This is a polar molecule. And it's a hydrogen bonding machine. So this being nonpolar, this being polar, well, that means that our polar solvent is going to dissolve the polar molecule, and our nonpolar solvent is going to dissolve the nonpolar molecule. And so we say that vitamin A is a fat-soluble vitamin. And we say fat because that's kind of like our, plants have oils, animals have fats. It's kind of the general breakdown of it. Because, plants are so much healthier. They just don't get fat. So we got a fat-soluble vitamin because it is a nonpolar molecule, just like our solvent. Alright, so water dissolves vitamin C, so we just call this a water-soluble vitamin. And you can say this about anything, if it's not a vitamin, we don't put vitamin on the end, but we can say that it's a water-soluble compound versus a fat-soluble compound. And so if we look at acetic acid, okay, we know it's water-soluble because it's right here, dissolved in water. It's vinegar. But does that make sense? Looking at that structure, does it make sense that this is a water-soluble compound? Does this look like a polar molecule to you? Hopefully it does, because we've got polar functional groups on it. This whole carboxyl group is a nice polar functional group. And yeah, we've got this non-polar area right here. But it's, at least 2/3 polar. Because this area is just as big as this carbon group over here, pretty much. So it's roughly 2/3 polar. So this is a polar molecule. It's only when, look at this. We've got a chain of, you got 6 carbons, 7, 8, 9 over here. You got our 1, 2, 3, 4, 5, 6, 7, 8, plus 2 more, 10. That's like almost 20 carbons before you have a polar area. That's like 20 carbons of nonpolar real estate. So it's a nonpolar molecule. And so why did I throw this example up? Well, nature's a jerk. I couldn't help it. I want to do vitamins. It's a nice clean-cut example. A lot of people are familiar with what a fat and water-soluble vitamin is already. I'm sure your nutrition class is covered if you've taken already. If not, you got a heads up on that class. You're welcome. You can just pay me a little extra. That tuition, that teacher can cut it off to me. That's fair. And so, yeah, this little bit, you really want to look at the big picture. If I take away this OH group, look at all that non-polar stuff. If I take away this OH group, that thing's still very polar. I take away that and that. I'm covering up almost the whole molecule to make it look non-polar. So that's a polar molecule. Same deal here. If I cover up the polar stuff, there's not much left. If I cover up the non-polar, look at how much there is. Look at how much that drawing still is. And so this is a polar molecule, which means that it is water soluble. That's all we do. We just go, is it water soluble? Oh, it is a polar molecule. If it hydrogen bonds, all the better. It's going to be even more water soluble. But water soluble is water soluble. Alright, so any polar molecule, anything like a hydrogen bond, which, you know, all hydrogen bonding molecules are polar. Not all polar molecules are hydrogen bonding. It's like the whole, like, all dogs are puppies. Wait, no, that's not right. All puppies are dogs, but not all dogs are puppies. That sort of deal. So, that's what we're doing here. That's what you do. You apply those attractive forces, and you have to recognize where they are in a molecule. Is it nonpolar? Is it polar? Okay, what about my solvent? Because maybe it's not water and oil. Maybe I use acetic acid as a solvent, or maybe I use something like ethanol as a solvent, or octane. You know, and you see the structure, and you'll probably do that in the practice homework and worksheets and stuff like that. You'll see this come up. But all it breaks down to is just IDing what is your solute and what is your solvent. Do they match? Yes or no? Like, these two aren't going to mix. But these two are, because they're both polar. This and this are going to mix, but this and this aren't. It's a mismatch. So you've got like dissolves like. That's what we're talking about. Non-polar gets dissolved by non-polar. Polar gets dissolved by polar. That's how it all breaks down. Now, being able to recognize if something is polar or non-polar, well, that is going to lean really heavily on the last section. So just a heads up on that. Alright, so next we're going to talk about ionic compounds and their solubility, which there's a few extra details there. So one more video and then we'll be done with this section.